All good.
Excellent. Thank you so much. Okay. Today I'm going to talk to you very much about process. So I'm going to talk about logic, equations, and data, and how to use each of them to complement each other to their best strengths in ways that allow us all to respond most usefully to a pandemic, whatever the nature of our science is. And now hopefully I can advance. Yes, huzzah. Okay. I'm going to put on my biodefense hat for a moment. For a little over a decade, I worked straight to the Department of Homeland Security in the area of biosurveillance and defense. And so I'm going to talk in terms of triage mode in that way. So in that sense, the biggest challenge that we all faced in the first month or two of coronavirus and ongoing since is how to make good decisions as scientists in the absence of information. So it's also important for policymakers to make good decisions in the absence of information. But since we're the people trying to provide information to those policymakers, hopefully we, before they, will make good decisions as we don't know anything. And COVID-19 is the epitome of what's called a zero-day threat, which means that you don't really have any anticipatory warning about the specific nature of the threat. You know, types of threats are possible and you can characterize them and consider them, but you don't know what the exact threat is until it's already upon you. And so COVID-19 is the epitome of a zero-day threat. And some really great science started almost immediately upon realizing that COVID was actually going to be a severe global challenge. Medical studies for pharmaceutical and non-pharmaceutical therapeutics, characterizing the etiology of the disease, the medical challenges, virological studies, some of which we've heard about already today, immunological studies, vaccine development started almost the minute we decided we had a pandemic, which is reasonably unheard of from the idea of pandemic response planning. And so as scientists, our goal really quickly is to understand what's going on, not just because we are curious, which is also true, but because we then hope to be able to make an impact on what's possible in terms of mitigating that threat for the globe. So, okay. So I'm going to advocate in all of this the use of formal risk assessment as a tool for triage in coordinating our own science and the science we do with others. So if you aren't familiar with formal risk assessment, it's incredibly simple. There are three main elements critical to any quantitative risk assessment, and you apply them however they work in the system you discuss. So the three main elements are to characterize the vulnerability, the likelihood, and the severity. And you use these separately, you piece them out, you disambiguate them in order to then be able to figure out how to plan against threats. And I'm going to argue today that we should also use them to decide which scientific questions to tackle, especially which to tackle first when we're faced with a new challenge. So what do they mean, first of all? So vulnerability is how easy is it for the threat to affect you? The likelihood is how likely is that threat to actually be enacted on you? And the severity is how bad is the outcome if the threat happens to you? Any two without the third leads to a potential misallocation of concern and effort. And humans are bad at this. We know from so many studies in social psychology and also just watching our own daily lives and the lives of those around us and our political leaders and in reading history and in appreciating art, that it's very easy to get fixated on the wrong aspects and combinations of what's risky. So we can worry about a meteor strike. The vulnerability of the planet to a meteor strike is very high, as is the potential severity of an outcome from a meteor strike. But luckily, 2 is quite small. The likelihood of any potential meteor strike is quite low. We could worry about a global pandemic of a benign cold, which is basically a case of the sniffles going pandemic. And actually, that has happened numerous times, and we don't really talk about it so much in pandemics because we don't care because the severity is so small. And we can talk about things like extinctions of pollinators. The likelihood is actually pretty moderate. We're seeing global die-offs in insects at least, and we have threatened pollinators in other species, in other genuses. But and the severity is huge, but the vulnerability for a single extinction of all pollinators at once is actually quite low because there would have to be a diversity of threats all enacted at once to hit that. So we can have these different combinations that are quite useful in terms of how to think about worrying and planning for threats. And the goal of splitting things up this way is to be able then to figure out which of the 3 elements at risk, if any, can be most effectively reduced, and then to put our efforts there. So it's not so much that we go, oh, well, if there's a small component, we don't have to worry about it. Small can still mean that the cumulative outcome of the threat is large. But where can we impact the process is more tenable once we split it up into these steps. And it's not just for advanced planning. So in the 3 cases that I proposed, those were all in the future. Let's think about how these things might happen. It's still true for real-time assessment and action in a 0-day threat such as COVID-19. So what do we do for pandemics? What does this mean? For a novel already emerging or emerged threat like coronavirus, a vulnerability characterization would be, what will a pandemic cause to fail? Likelihood will be, how likely is it that the pandemic will cause it to fail? And severity would be, how bad will it be for someone or everyone if it fails? Now notice there is a whole field projecting how likely a pandemic is, or how vulnerable we are to a pandemic, or how severe a generic pandemic would be. I'm not talking about that. I'm now talking about literally today, we know coronavirus is the threat. How do we now shift our science in order to address questions that will let us mitigate it? And that is about the impacts of coronavirus, not coronavirus itself, which doesn't mean that those questions are not best answered by understanding the nature of coronavirus in new ways. So for vulnerability, here's where it's going to start being incredibly clear that I work at a really different scale of biological organization from almost everybody else who's talked at this whole conference. So when I'm talking about what will a pandemic cause to fail, I'm thinking about things like healthcare resource availability, the movements to do things like flatten the epidemic curve, isn't so much about making sure that nobody catches coronavirus. It's about making sure that we have access to the medical resources and understanding to take care of people so that if they catch it, they wind up okay. And that's about delay and limitation in magnitude at any one point in time. And sometimes those mitigations sacrifice an overall a number of people affected. We can actually accept an increase in the number of people affected, so long as we don't do it all at once and we don't do it early. So the vulnerability of our healthcare resources is very high. It's very easy for those to be affected by the pandemic. It's the safety of available water. If you lived somewhere where safe water was available before the pandemic is unlikely to compromise your water safety right now. That didn't have to be true. If this had been a global pandemic of cholera instead, we would be having a whole different conversation. There are entire economies at the level of the globe, nations, subnations, regions, even local municipalities that depend on in-person interaction, and each of those have a variable vulnerability to impacts from the pandemic. The function of densely populated venues, so schools, nursing homes, churches, sporting venues, the vulnerability there is very high, right? And these are very easy to characterize, where you don't have to do a lot of thinking. That's part of the power of splitting it up this way. Each one you can just go low, moderate, high. Okay, great. And if you want an exact calculation, it can take more work. But if you want triage, and I would argue that for a 0-day threat, most of what we should all do is triage. Triage is very useful to have at these broad categorical sweeps. All right, likelihood is still challenging. Estimating the likelihood of each of these things is complicated. How likely is it that the pandemic is going to cause healthcare resource availability to fail? Almost instantly, there were a zillion epidemiological prediction models saying how bad will the epidemic be in which region of the globe when. And those specifically helped us understand the likelihood of healthcare resource overwhelm, surge capacity. Those were critical in my being able to say to you here today that the likelihood of this is high. Not just the vulnerability, but the likelihood. I didn't need a lot of modeling to tell me that the likelihood of water safety availability is very low. Again, the vulnerability is separately low, but the likelihood also very low. Not impossible, but low. The economies, again, are going to be moderate or variable, depending on the specifics of the scale and scope of the question. And the function of densely populated venues, again, the likelihood is high, and that's literally because of the nature of interpersonal transmission of infection. So now not just the vulnerability, but the likelihood. If we go to severity, again, now we can just broad brush everything. Again, this isn't as difficult to characterize. There's still some good modeling tools that we can use in order to make rigorous quantitative assessments. But triage level, if we hit surge capacity and exceed surge capacity in healthcare resources, that's terrible. If we run out of personal protective equipment for doctors and nurses, that's terrible. We should avoid this if we can. What's the severity of a coronavirus compromised water safety compromise? It's probably regional. It's probably pretty localized. It's going to depend. Even if we find somewhere that was, even though it was very low vulnerability and low likelihood, if we get all the way to, but it happened, how severe will the outcome be? Not great, but probably not bad. Economies, again, it depends on what we're talking about. Function of densely populated venues, yeah, it's probably going to be terrible. Now, if you'd asked earlier in the outbreak, we might not have said terrible. We might have just said, oh God, it could be very bad, but we don't know. It depends a lot on the mode of transmission. Now that we have a better understanding that fomite is not really driving the outbreaks as much as we were worried it might, but that droplet and now even more, we're thinking maybe aerosol might. Now we're going, oh God, dense is bad. Dense has never been good, but dense is potentially as terrible as surge capacity. All right, so how do we pick a best first problem from all of this? What do we do? Now that I've sort of made you guys walk through with me what a formal risk assessment looks like for the impacts of coronavirus. Now how do we use that as scientists to go, what do we do? Well, it's not clear from this table. If your answer was, I don't know yet, good job. Because there are some things that look like we should put our energy into them. Just going across the board for healthcare resources, right? High, and terrible seems pretty bad. High, and terrible seems pretty bad. So it seems like we should be looking in dense venues and healthcare resources more than in safe water and the economy. But, there's a huge but, there is that question, what can we affect? Not what can we understand, but what can we actually affect if we were able to understand it? If rapid response science gave us an answer, what could we go do in the real world as a result? Now we have some targets. Now we have, okay, if dense venues are highly vulnerable, the likelihood of the impact is very high and the severity is terrible. Of these three, which one is the easiest one to change? Maybe we could decrease the vulnerability by decreasing the density. If we had the ability to increase the capacity or production of resources for healthcare, we could impact the likelihood of healthcare resources being compromised by coronavirus. If we had some stimulus and security, we could mitigate economic severity. Each of these are things that we can now talk about. Should we do them and how should we do them? And instant answers in science are no less scientifically meaningful for the rest of this table, but they might be a little bit later on in the progression of the urgency for when we might need to answer. So what are some, I sped ahead. So let's focus on one of these threats. And I'm going to focus today with you on decreasing density in high density venues. And I'm going to specifically talk about decreasing vulnerability, although I'll also make passive mention of likelihood and severity as I go. So what are the typical dense venues? Okay, schools. Schools across the globe instantly became remote or shut down really fast. Nursing homes for the elderly and infirm. Almost no one knew what to do. You can't shut those down. Where do people go? They require medical care. And they require caregivers, none of whom may be instantly available or any more safe. So at least in the US, instead of focusing on the lowest hanging fruit, which was reducing the vulnerability, because it was impractical, instead we instantly went with likelihood. And what we did was prohibit visitors. That's not great, but it's a reasonable next step. It's a good best we can do action. Places of worship almost instantly got shut down or became remote. Sports arenas almost instantly shut down. Prisons. All right, so if you're not familiar with the utterly depressing state of incarceration in the United States, the next couple of slides are terrible and true. 0.7% of the United States is currently incarcerated. That's insane. But we're not going to talk about whether or not that's insane. We're just going to talk about coronavirus. This graph shows the number of incarcerated adults per 100,000 Americans, excluding federally incarcerated inmates. So this is just state. In my own home state of Tennessee, prisons are incredibly crowded. They are over their occupancy rates, in some cases by 150% of the legal occupancy or more. And in case you were wondering, jails and prisons have never been spacious. So occupancy rates are set at a minimum, I believe, by about the Geneva Convention. So when we say that we're over 150% capacity, frequently we're talking about the number of people per available bed, which means that it is not uncommon for jails in the United States and including Tennessee to have people sleep on air mattresses on the floor in cells meant to house two people in a bunk bed, basically fitting the air mattress or plastic, not even an air mattress, it can also just be 2 inches of plastic as a cot next to the toilet. None of this is good for preventing disease transmission. Incarcerated populations are also really unhealthy. If you weren't unhealthy as part of a lifestyle that lent to you being more likely to be convicted and incarcerated, being in a jail or prison for any length of time in the United States is enough to cause compromised health in the vast majority of incarcerated people. To the extent where I found a graph for this. This graph is taken just from a study of the cardiovascular complications of incarcerated populations, but there are some compelling studies that say that after 6 months of being incarcerated in a prison in the United States, most people are functionally immunocompromised simply by the stress and conditions of the prison facility. Medical estimates of outcomes of severity, not having to do anything with coronavirus, just writ large, of all medical complications. It is a good back of the envelope calculation if you're trying to prognosticate how well someone will do from in treatment or progression of any particular illness, to assume that they are 10 years older than their actual physiological age if they have been incarcerated for any long length of time. So we're not talking about a healthy population. So we're talking about a very large population, 0.7% of the United States. We're talking about a very densely packed population. We're talking about a population that's predominantly unhealthy. And people don't stay in prisons. So even if we wanted to be incredibly calloused, which I would not argue we should be, and say that this is a problem for the incarcerated population, but not the rest of us, 200,000 people are in and out of jails and prisons in the United States every week. That's due to the natural churn of our criminal justice system. It's due to people who enter correctional facilities in order to provide legal services, medical services, and who are actually staff of the facility itself. None of this lends itself to containment. So, going back to the process, going back to risk assessment and triage and what can we affect. So instantly, as wearing my pandemic preparedness epidemiologist hat, as soon as COVID struck, a bunch of my friends and I, my colleagues and I went, okay, what can we impact that's going to provide meaningful risk? We used that risk assessment and we said, high density populations where we don't have other ways to mitigate the risk. Maybe reduction of density as a way to reduce vulnerability is a good way to protect everybody. So we considered first the logic of the system. So now this is where my talk title came from. Bear with me on that. So we considered the logic of the system. From that, we identified the target risk we thought we could impact well. Now it was time to go from the logic of the system to a quantitative set of equations. So what do? One of my things that I love doing is I'm an epidemiological modeler. I have lots of different tools for this, and I'm absolutely not going to make you walk through the 67 different differential equations that we wrote for it, because I'm hoping, because even though this is a remote talk, I am worried one of you will find me and hurt me. So instead, here is the flow chart of the model. And each of these, I don't know if you can see the resolution on the screen, but these are meant to seem layered because there is a layer of these layers of these categories for low risk adults, high risk adults, and this is by simply by health. Are you diabetic? Or do you have hypertension? Are you obese? And elderly adults. And then of course there are also children. And then while they are members of the community, we separated out jail staff. And we did specifically tailor this model to jails rather than prisons. The only functional difference is the rate at which people go through processing in court and get released back into the community. Okay, so then there are, in fact, the people who work in and circulate among the criminal justice system in the United States. Oh, thank you for the teddy bear. I don't, that is awesome. Anyone talking about the criminal justice system of the United States for too long could use a teddy bear, so I appreciate that. Thank you. Dealing with the processing and court system is unlike the community and unlike the carceral facility because the density of people within that system is very different. And of course, by epidemiological modeling risk, we know that the rate at which individuals come into contact with each other and the closeness of that contact alters risk. Oh, thank you for the question. Yes, I defaulted to assuming more epidemiology than I should. The epidemiological categories are susceptible individuals who can catch the disease, exposed individuals who have already caught the disease but are not yet showing signs and symptoms. They may be, we know for COVID that there is potential for pre-symptomatic transmission. So in this model, our E class includes pre-symptomatic transmission. The I class, where they have begun, where they are definitely infectious, but have also begun to demonstrate signs and symptoms themselves. And the recovered class or removed class, which includes also death, where people have at least short-term immediate immunity so they cannot instantly recatch the disease. And then if you are infected, you can be removed to a medical facility. So that includes hospitalization, hospice care, urgent care clinics, anything that will remove you from general circulation from the community, but provide you with access to medical care. Thank you so much for the question. And that will repeat in the different subcategories where M in this case defaults to the medical community, the medical resources to the community, but the M inside the jail, the first pass of triage is a medical care facility within the jail. And then it is assumed that if you are in need of hospitalization, that you will be transferred to a hospital. It is assumed in our model that hospitalization is good at isolating you enough that you do not then infect members of the broader community. That's a pretty strong assumption, but we decided that if hospitals were seeding the rest of humanity, we had truly failed in all possible personal protective equipment and triage mechanisms. So, okay, and then of course people can be arrested from the community and go through the processing system. They don't actually arrive directly at the jail. There's intake process that has to happen, and then they're brought into the jail if they're arrested. But the jail staff does come and go directly from the jail. When people are released from jail, either because they have posted bail or because they have finished serving their time in and have been released, sometimes the prosecuting attorneys will decide not to go to trial. And so people are released because they're completely done with the criminal justice system, or they can be released on their own recognizance and they're meant to come back into the system for trial at a later date. Okay. Hopefully that explains all of the pieces of our epidemiological model. Again, I'm not going to show you the math, but it is available. The paper presenting this is on medRxiv. The data challenges from those zero-day threats are immense. So now we're moving from, we talked about the logic, and then we went to the equations, and now it's time for data. And data is about where everyone else that I've talked to at this meeting comes in. How do we know what's happening? How do we estimate things we know happen but can't measure? How can we make recommendations without waiting to see how the threat plays out? This is the biggest one. All of the things for a standard epidemiological model rely on there having already been an outbreak to analyze. When an outbreak is currently happening, what do we do? And I would argue we go right back to risk analysis. Usually the sensitivity of models, especially differential equation models, is done post hoc. You produce the model, you parameterize it, you analyze it, and then you figure out the sensitivity. For 0-day threats, that is exactly backwards. The correct steps for building useful models during emerging threats is to hypothesize your logic. Build your model as a logical hypothesis. Make best guesses based on whatever bad data you've got. Then run a sensitivity analysis without analyzing the outcomes of your model. Figure out which data could be improved upon that would impact the outcome of your model. And then run your model and make recommendations, with huge disclaimers saying you don't know enough to really hammer this out. Here is just one subset of the number of parameters we needed to estimate for this jails model. Some of them are impossible to know. So for example, the % reduction in transmission during the asymptomatic or pre-symptomatic period of infection. As COVID is developing, we can't know that. We can only know that as the outbreak itself progresses. For these, we run the model over a range of options and just move on. We can't estimate them well. For others, there is bad data. We know that China is not like the US, that the general public in China, in Wuhan province, is not like an incarcerated population in the United States. We still used a best guess approximation of data fit from China in order to get, in this case, the proportion of patients with viral shedding for the pre-symptomatic and asymptomatic patients. What do we find? I'm going to hurry up because I want to leave some time for questions. At the time, this was a prediction. It has since happened, so we feel like we did a good job, which is frankly terrible. Our predictions from the model were that we would get gigantic instantaneous outbreaks in jails, and that those would anticipate but be followed by outbreaks in the community that were in part seeded by released infected people from the jails. So the important question from that is actually, how does this help? So remember that from earlier, the reason we were doing this was to try and evaluate whether or not decreasing density could mitigate threat. So now we can use this model to see whether or not decreasing density may actually help. There are two ways to decrease jail density that are in keeping with the Constitution of the United States. One of our reviewers was very upset that we didn't actually suspend all due process of law and just lock the doors on the jails. Can't do that. We could decrease arrests by saying that anyone who commits a minor crime might be issued a fine or be told that they have to show up back at a trial but not be put in a jail. Or we can release people early from their sentence as long as we feel like they're not a threat to the community. So we contrasted each of these strategies under some different scenarios that I frankly won't go through in the interests of time, but they involved a baseline of the community is sheltering in place, but we do nothing with the jail, all the way to we arrest fewer people and increase the release rates at the same time of lots of people in the jail. And I don't know if you can see the light blue dots, but the impact to community infections, the incarcerated population itself, and the staff of doing all of those together is a dramatic decrease in risk. In severity, I should say. So that what we're doing by mitigating the vulnerability is affecting the full progression of both the vulnerability and the severity. We can reduce the severity over the entire community. Here is just as we decrease the jail density. If we just look at it as a reduction of contacts, that's just the vulnerability. What do we do to the severity? And you can see the progression from we haven't done anything to we've allowed the jails to be sparse enough that they now mirror community contact. Based on this model, we instantly made recommendations to criminal justice agencies. We filed lawsuits on behalf of the incarcerated population. And even more importantly to the community, we gave hospitals near carceral facilities time to prepare for a spike earlier than their community would otherwise have anticipated. So back to the process. We considered the logic of the system. We identified a target risk we thought we could impact. We made our logic into equations. We used those equations to identify data gaps. We approximated the data badly. We interpreted the model outcomes, and we made real-world recommendations in real time. Critically, in the United States, the first death that we thought about at the time, we've since revised that to be earlier, was February 29th. We had the first guidance for social distancing on March 16th. This model and its findings were published on medRxiv on April 14th. So this was really quick and dirty. Did we get it right? Scientifically, almost certainly not. Although our predictions for the within jail spread have actually come to pass pretty closely. But we got it right enough to help. And I would argue that right now as scientists, that's actually our best practice. Many of the data gaps for this study and others are low-hanging fruit for computational biology. And so I would invite you guys, I would love it if as a community, computational biologists lent towards triage, not just the best scientific questions, but the most useful right now. There's a wonderful quote by Asimov that to brighten the light of science anywhere is to brighten it everywhere. And that is always going to be true. But sometimes it helps to brighten it faster in some places before others. All right, these are my wonderful collaborators circled in red on the actual jails project and the rest of my lab because they're always awesome. And with that, I think we have 6 minutes for questions.
So, Jana, did you want to share this part or did you want me to do that? I guess I will do it. So I'll start with, before I look up the questions.
Oh, sorry.
I was going to say, before I look up the questions that were actually posted, I was going to ask my own question, which is that avoiding to go down the political quagmire and rabbit hole. So how much is the percent testing? And so I think in the incarcerations, in the jails, the testing has been pretty high actually, right? But in other places, some of them?
Well, so it's incredibly variable. In the United States, jails, so prisons can be either state or municipal. Yeah. Jails are municipal.
Okay.
So it's city by city. And the testing is really variable. It goes all the way from, some jails have claimed that they have tested every single inmate. That turns out when you poke at it not to be quite true, but it's much better than the jails that are, there are some jails that are only testing essentially people who might need to be hospitalized.
Yeah.
So
that's going to affect all of your modeling and everything, right?
Yes and no. So again, in terms of exactly that risk assessment, what can you impact? If testing doesn't result in the removal of an incarcerated person, and frequently the jails are so full that there's nowhere to isolate someone who would test positive. So all you're actually doing epidemiologically is mitigating the risk of that person's death by being able to anticipate their medical needs, but not being able to interrupt transmission. Testing doesn't do much in that case.
Okay. Let me quickly go look at the Q&A. I don't see anything there right now. So from, and we have, just so you know, we have over 100 people in the room, so.
Oh goodness, thank you all for staying.
Yeah, it is the end of the meeting though.
Yeah.
And so, I'm going to ask actually Jana to maybe jump in right now while I look up at the other questions. Possible, I look at the, there we go, Q&A. There we go, there's some stuff in the Q&A.
So I had a question that I can ask, I guess, out loud. I put it into the chat, Nina. Thank you so much for a wonderful talk. Just a generic, maybe simple, maybe not. Is there anything that we, the more molecular biology oriented people, can do to inform your models? Maybe to help answer the real life questions rather than sticking to, you know, the further along questions?
Yeah, absolutely. So thank you. Yes. So part of the answer to this is unfortunately going to be that what we need actually is communication and collaboration to identify the question, because I don't actually know all of what you are capable of doing molecularly. And potentially you guys don't know which molecular questions would be useful epidemiologically. So for example, if there were a way to identify a protein that could interrupt transmission just among densely packed populations, if there, for example, is a dose response curve to the severity of infection that we now suspect epidemiologically is true, if we could identify anything molecular or protein structure for that, that we could understand at all how to interrupt, even if it doesn't prevent a wide-scale outbreak in the community, that would allow us in high-density populations. This is a naive answer because I don't truly understand. I have been talking to a molecular person who has been telling me something like that is possible, and my answer is I don't get it. So it's an unsatisfying answer to give you. I apologize. But the answer is yes. I would assume that there are a lot of those in that list, that giant table of parameters that I showed you. None of them are well known. If anyone would like, I would love it. I would love to follow up and discuss any of those. If anyone would like to talk to me or to read the paper on medRxiv and look at them and say, oh, I have better insight about this one. We've also published in the medRxiv data the sensitivity of the model outcome. So you can see if refining that to a better answer would change the policy recommendation. I would argue that that's the sweet spot. If you can look at it and say, we can get you a better answer, and it seems like that answer would change the recommendation of your model. Those are the ones.
So Ido Freeberg asks, he first commented it was a great talk, so thank you very much. We now understand the threat of COVID-induced long-term morbidity and increased mortality on the overall population wellness and the economy. If you're looking at the risk assessment over the next decade, does that change anything?
Oh, what an awesome question. It absolutely does.
Ido's an awesome guy, so.
Yeah. Okay, good. In that case, I will know not to be surprised.
Yes.
Yeah, that is an awesome question, and it does change the risk assessment, but all of risk assessment is geared in what it is you're trying to mitigate. So for example, if you're trying to limit the number of deaths, you might sacrifice to allow more people to become infected. If you're trying to minimize the decrease in quality adjusted life years, you may actually accept greater, over a whole population, you may accept a greater number of deaths in order to interrupt transmission. There are some diseases, COVID is not one of them, where you will do anything to prevent it getting into children because children who catch it will just die. So you might think of just one segment of the population that you want to protect. You might want to protect economic impact. You might want to make sure that no one ever exceeds surge capacity in your medical facility regionally. Each of those is a different threat assessment. So in terms of triage for pandemic preparedness, we're trying to think of as many different cases, and you do that threat assessment for as many of them as possible and then hit the low-hanging fruit fast. But you're absolutely correct that all of this changes when you change the target.
So Howard Cash asks another question: would your approach change if there was an assay that measured likelihood of severe medical outcome? How would it change if one knew that M inmates were likely to get mild cases and N were likely to have severe fatal outcomes? Assume all are likely to transmit.
Absolutely. So what you've just described is a mixed objective function optimization process, which is actually, of the few times in the world, if you happen already to have modeled your system as continuous differential equations, then it is occasionally possible. You have to prove uniqueness and existence first, but it is occasionally possible to figure out optimal control strategies for multi-objective functions. And in this case, the multi-objective function that you would suggest would try and minimize severe cases and potentially transmission for a mirrored estimate of severity in the community. But yes, so, and also, of course, tying back to the last question, what you've really done is shift what the target is, which is, again, a brilliant and important thing to point out. But we do actually have a way to target how to shift control when your target shifts to include multi-objective functions if such an assay were developed. So if you guys can do that, yes, please.
So a quick question, Chris Sadel asks, do prisoners wear masks?
Oh, we wish. That would be the greatest thing. So right now, prisoners don't get given soap, much less masks. The declarations from incarcerated people throughout the United States have included such wonderful things as, I purchased an extra pair of briefs, of underwear, underwear, and made my own makeshift mask out of that. But because I wasn't given my ration of soap this week, I've been wearing a dirty underwear mask on my face for a week without being able to wash it.
Okay. We're actually over time, and so we've got to get back to our schedule. So thank you very much for a great talk, and we really appreciate your contribution to the ISMB 2020, albeit if it was a virtual one. Would have been nice to see you in Montreal, but